Good day to everyone. Today our group will be presenting about our project titled Design of a Solar PV based cooling system for a typical Malaysian primary school in Ipoh. First, I would like to introduce the members for our group, which is group 4. There are 5 people altogether, which are Dhashneswaran, Rishen, Qayyim, Dayalan and Raziq. In this presentation, we will explain about the introduction of our project, consists of the project background, problem statement, objective. Next, we will explain about the methodology, results, feasibility, tools, and finally the conclusion. Moving on to the background of study. In recent times, the growing emphasis on energy efficiency and sustainability has spurred the investigation of renewable energy technologies to cater the cooling requirements in buildings. Tropical countries like Malaysia, in particular, face a pressing need for efficient cooling solutions in educational establishments due to the challenging climate conditions prevalent throughout the year. Ipoh, a city characterized by warm and humid weather, encounters difficulties in creating comfortable learning environments for students attending its primary schools. Malaysia possesses abundant solar radiation, which makes it conducive for harnessing PV technology to generate electricity. However, the drawback lies in the fact that high temperatures in the region can diminish the electrical efficiency of PV panels. Consequently, the cooling of these panels becomes a critical consideration. Prolonged exposure to elevated temperatures can lead to both short-term and long-term degradation of the PV cells. So, the objective of this project is to design a solar PV-based cooling system for a typical Malaysian primary school in Ipoh. Also provide detailed design and calculations for the proposed system. Moving on to the literature review. Solar PV refers to the technology that converts sunlight directly into electricity. It is a clean and renewable energy generation method that harnesses the energy from the sun using semiconductor materials, typically made of silicon. When sunlight strikes this PV cell, it excites electrons, creating a flow of electricity. The basic building block of a solar PV system is the solar cell, which is a small semiconductor device that captures photons from sunlight and converts them into electricity through the photovoltaic effect. Multiple solar cells are connected together to form solar panels, and these panels can be installed on rooftops, ground-mounted structures, or integrated into various surfaces, such as building facade or solar farms. Solar PV system can be categorized into two main types, which is grid type and off-grid system. Using solar PV technology offers numerous advantages, making it a highly favorable renewable energy solution. Some of the key advantages of using solar photovoltaic system are its clean and renewable energy, reduced carbon footprint, energy independence, and lower operating costs. In conclusion, this project has met its objective in terms of the design and its feasibility. The cost of electricity bills can be reduced and the system has a very optimum payback time, which is less than 10 years. Since the solar system components such as photovoltaic panel, batteries and solar system controller present in abundant in the market, the development and execution of solar system has becoming lower in price tag, while giving clean and optimum power source to the users.
Moving on to the methodology, I'll be talking about the design tools and software. So in this project, we use two softwares, which is AutoCAD and SketchUp. So AutoCAD is primarily used for 3D and 3D drafting. And AutoCAD has a robust set of features and versatility, making it an invaluable tool in the design industry. So in our assignment here, the software was used to create a solar PV design, and it was used in the 2D and 3D drawing. The title block was also created using AutoCAD. Moving on, the second software is SketchUp, where it is a 3D modeling software, and it is known for its user-friendly interface and intuitive tools, making it accessible to both beginners and experienced users. SketchUp was used during the sketching part and also during the visualization of how the solar panel will be on the school building. moving on to my results and discussion, I'll be talking about the detailed designs. Here, in the design of the solar panel, we decided to use the monocrystalline silicon cells, which has the highest efficiency among the photovoltaic cells. The efficiency is around 15 to 20%. Although it is much more efficient, it does cost slightly more to produce. So in our project here, the size of each panel is about 2.584 meters squared. And with our calculation, it will occupy about 68 meters square of roof space. Okay. The solar panel will help generate electricity to help cool down the school building. And with that being said, the average monthly consumption for primary schools in Malaysia is around 1,568.7 kilowatts per hour. So with our calculation, it takes about 26 solar panels, therefore leading into the 68 meters square of roof space being occupied. So hopefully with the solar panel design, we'll be able to support and fully cover the cost of cooling the school building. Then moving on to the last part, this is the drawing design. The last part was drawn using SketchUp, and this is the 3D drawing that we used in AutoCAD. So solar panels can lose their efficiency, and there are many factors that affect this, but one of the main reasons is because of increase in temperature. So when the temperature increases, the efficiency of solar panels also decrease. In our design here, we have made a slight improvement to improve the current design and to maximize the efficiency. So the first thing we made is a mounting bracket which can be adjusted. With that being said, the bracket can be adjusted so that the solar panel is facing the sun, because different schools are in different locations and have different solar irradiance, meaning we would need to adjust the placement to get the most out of the sun to convert it into energy. Other than that, we also decided to improve the solar panel cooling rate so that there is less efficiency drop. So the first form of cooling is by having water flow in water tubes, which is located behind the solar panel. And this will help cool the solar panel even though they are under the scorching hot sun. And to further add to the cooling power, we decided to add a few small fans behind the solar panel. This will help circulate the air under the solar panel and remove heat. As said earlier, heat is the major factor in the efficiency loss. So hopefully with the panels being constantly cooled, the temperature will not rise and affect the efficiency. So hopefully this will help us produce the most efficient solar panel.
Hi, my name is Dhashneswaran and I'll be presenting about the methodology for this project. Firstly, it's about the material selection. Monocrystalline panels are chosen for their superior efficiency compared to other panel types. These panel feature cells aligned in a single direction to enable them to capture a substantial amount of solar energy and convert it to electricity. Monocrystalline panels are crafted using monocrystalline cells made of pure silicon. This purity contributes to their higher costs, but it also enhances their efficiency in absorbing solar energy, meaning fewer panels are required to generate electricity. The smaller solar cells and distinctive orthogonal shape of monocrystalline panels make them an ideal option for installation with limited available roof space. Properties of materials. The photovoltaic system is typically designed to remain functional for a minimum of 20 years, making the selection of appropriate mechanical components crucial during this design phase. The mechanical design for the PV system consists of these following aspects. Firstly, analysis of mechanical forces. This involves identifying and assessing the forces that act within the system. Secondly, structural members. Careful selection, sizing, and configuration of structural members are necessary to support the overall layout of the PV system. Material selection. Choosing suitable materials is important to ensure they can withstand the system long life cycle without degradation. Mounting position. Properly locating, orienting, and mounting the PV array is essential to maximize excess sunlight and generate the required electrical output. And finally, design and support structures. Pleasing support structures should be integrated into the site and application to facilitate easy installation and future maintenance. This table shows the important material properties for design of PV system. Firstly is the mechanical properties, which consist of hardness, modulus of elasticity in tension, compression, Poisson's ratio, stress strain curve, yield strength, and also tension. For the thermal properties, it consists of specific heat, conductivity, emissivity, absorptivity, fire resistance, and also ablation rate. For the physical properties, it consists of crystal structure, density, melting point, vapor pressure, viscosity, and porosity. And finally, for the chemical properties, which consists of corrosion and degradation, atmosphere, salt water, acids, hot gases, and ultraviolet, position in electromotive series, thermal stability, stress corrosion, hydrogen embrittlement, and finally hydraulic permeability. The selection of mounting panels and structural members is important based with the provider design guidelines. Firstly, choose materials that exhibit sunlight or UV resistance suitable for outdoor application. Utilize sealants, particularly urethane-based ones, for non-flash roof penetrations. Ensure that materials are capable of withstanding the surrounding temperature. When installing materials that are dissimilar, use non-conductive shims, washers, or other methods to separate them. Avoid direct contact between aluminium and concrete materials. And finally, select fasteners that meet the specific standards and specifications, such as stainless steel. Moving on to the next point, which will be the market share. In 2013, monocrystalline solar cells accounted for a substantial market share of around 36%, according to the Fraunhofer Institute photovoltaic report in 2014. Monocrystalline solar cells produce an impressive of 12,600 megawatts of photovoltaic capacity during that year. Even though holding a significant market share and high production capacity, monocrystalline solar cells rank as second, with polycrystalline silicon technology claiming the top spot in the terms of the overall market dominance during that period. Efficiency and feasibility study. Monocrystalline silicon cells lead the commercial photovoltaic market with laboratory efficiency reaching an impressive of 25%, surpassing other options like polysilicon, CIGS, CDTE, and A-style cells. Solar module efficiency for mono-Si exceeded the 20% milestone in 2012, showcasing a remarkable 5.5% improvement in the technology's performance over a decade. The reduction in silicon water thickness for solar cell manufacturing has led to greater resource efficiency, which contributing to a decline in solar prices and making solar energy a cost-effective and sustainable solution for meeting global energy demands. And for the feasibility study is to analyze and evaluate the potential of this PV system used in this project. Technical feasibility. Utilizing of single highly pure crystal. Monocrystalline solar panels are known for their utilization of a single, exceptional pure crystal of silicon. This high purity level is achieved through a specific manufacturing process that ensures the silicon meets the string requirements of the solar cell industry. Czechoslovak growth process. The manufacturing process involves the Czechoslovak growth apparatus where a silicon seed crystal is immersed in a melted polycrystalline silicon. As the seed crystal rotates, it forms a cylindrical ingot of highly pure silicon, which will later be sliced into wafers. Control phosphorus doping. The wafers are heated in the presence of phosphorus gas to create a uniform junction of the proper depth. This process, known as phosphorus doping, allows for effective penetration of phosphorus atoms into the porous silicon, enhancing the electrical properties of the solar cells. And finally, precision and efficiency. The careful control of temperature and time during the manufacturing process ensure the uniformity and precision of the solar cell structure. This precision contributes to the higher efficiency and performance of monocrystalline solar panels, making them a popular choice for various applications in the solar energy industry. Longevity. Monocrystalline solar panels as first-generation solar technology have proven track record of remarkable durability and longevity. Monocrystalline solar panels have even endured the demanding conditions of space travel, showcasing their ability to withstand extreme environments and maintain functionality. Studies indicate that monocrystalline panels experience a gradual decrease in efficiency, average around 0.5% per year. While the decline occurs over time, they can continue to produce electricity effectively for an extended period. Despite their long-lasting nature, there will eventually come a time where the declining efficiency makes it economically viable to replace the panels, especially as the newer panels continue to improve their efficiency. Most monocrystalline solar panels come with warranties that extend up to 25 years. Proper maintenance, such as keeping the PV panels clean, allows monocrystalline panels to generate electricity even beyond the warranty period, maximizing their lifespan and benefits. As the solar industry advances, newer monocrystalline solar panels are likely to achieve even higher efficiency, making them an attractive choice for future installation and replacement. Efficiency. SunPower, a US-based company, leads the industry in manufacturing the most efficient monocrystalline solar panels, achieving an impressive 22.5% efficiency. In July 2010, SunPower set a new record for commercially produced solar cells at 24.2, showcasing their remarkable progress in the field. While theoretically achieving more than 29% conversion rate for the light into energy using crystalline solar cells seem unlikely, real-world applications suggest that practical limit for PV panels is estimated to be around 24 to 25% due to factors like heat. Monocrystalline solar panels have unique ability to convert the highest amount of solar energy into electricity among all types of flat solar panels, making them an excellent choice for maximizing electricity generation within limit areas such as rooftops in urban settings or places with limited space. Energy consumption during manufacturing. Thin film solar panels have a lower level of embodied energy per panel, but this advantage is somewhat offset by the need for more panels, especially when additional mounting rails are required. Embedded energy refers to the total energy consumed in the manufacturing and supply of a product. Enhanced heat resistance. Monocrystalline solar modules experience a decline in output as sunlight raises the temperature to approximately 50 degrees Celsius. The efficiency loss observed in monocrystalline panels due to the heat is lower, ranging between 12 and 15% comparing to PV panels made from polycrystalline cells. Finally, increased electricity generation. Monocrystalline panels produce more electricity per square meter of installed panels, leading to reduced electrical bills and electricity sales and improve cash flow for users. These panels contribute to environmentally friendly practices by reducing the demands for electricity from local power plants, leading to decreased reliance on fossil fuels and a reduction in greenhouse gas emission. Credibility for financing. The durability and longevity of monocrystalline solar panels have established strong performance records in certain regions, such as Germany. As a result, people in these areas can secure bank financing of up to 90% for their solar projects, expanding Germany's position as the largest installed base of solar panels worldwide. Environmental viability. Monocrystalline solar cells are manufactured from a single, exceptional pure silicon crystal grown into an ingot through the Czechoslovakia process and then sliced into these thin wafers. Being one of the oldest and most reliable methods of harnessing solar energy, monocrystalline cells have proven to be environmentally safe and free from any hazardous or harmful impact on the environment, as affirmed by reputable companies like Pyro and Bosch Energy. Moving on to my final slide of this presentation is the economic feasibility. Solar panels typically account for about 60% of the total expenses when considering the cost of a fully installed solar power system, with installation being a significant cost component. Homeowners have reported cases in Australia where they had to replace thin film panels at a loss to upgrade to more efficient monocrystalline solar cells to meet increasing electricity needs over time. The emergence of electric cars and the expected increase in the market presence may drive up the demand of high-efficiency solar panels to facilitate electrical car charging. Fuel cell-based vehicles such as Honda's hydrogen car under development may also contribute to higher electricity demand for small on-site hydrogen pumps, powered by solar energy generated during the day. To prepare the potential technological advancement and the increasing demand of the electricity, it is advisable to plan and generate as much as electricity as possible from the designed solar panel area. Considering the world's rapid transition to renewable energy sources and advancement in transportation, among other factors, the type and scalability of the solar array used may influence house prices in the future. Thank you.
Hi, my name is Dayalan, and today I'm going to talk about the installation process of this methodology for our project. And now starting, we have the preparation. Before proceeding with the planning and installation of PV modules on the roof, it is highly advisable to create precise roof plan. This plan should include detailed measurements of the roof dimensions, surface area, height, and the position of existing fixtures and superstructures. Considering shading is of utmost importance in the PV array installation process. To ensure the entire array remains unshaded from 9 AM to 5 PM on the shortest day of the year, a shading analysis must be conducted by the designer. This analysis helps determine the ideal mounting angle and the best location for the PV array. Manufacturers of the mounting system usually provide like a detailed table calculation to aid in making these determinations. In addition, the installer must take responsibility for designing an electrical wiring diagram that encompasses all the electrical components, including string wiring and the inverter's placement, and the necessary PV combiner junction box. Next, we have the attaching roof hooks. Attaching roof hooks. To begin with the PV module installation process, the installer can use chalk or other suitable markers to draw the position where the modules will be placed, ensuring an accurate layout. To facilitate the installation of roof hooks, the roof tiles are temporarily removed, providing a clear view of the roof structure's rafters. This visibility allows the installer to drill precisely at designated point on the rafters. For proper hook placement, the hook legs are positioned over the wave through the roof of the tile below, while the mounting plate spans the entire width of the rafters. To ensure the secure attachment, the installer must use screw with appropriate specifications and dimensions, such as a minimum screw diameter of 8 mm and a length of 80 mm. By following these steps, the installer can efficiently securely fit the PV system onto the roof structure. Next, we have the fitting the panel stand. After installing the roof anchors or penetration mounts, the solar panel is secured on the horizontal pole. It is then positioned over the mountain anchors, ensuring proper alignment with the intended orientation and tilt angle. If using a stand, the base is attached to the plate or mounting bracket securely to the roof anchors using suitable hardware. For a horizontal pole, it is placed firmly on the mounted brackets or clamps. All the connection is secured to ensure stability and checked for level alignment. A load test is also conducted to assess its capability to withstand the weight of the solar panels and also the external forces. This crucial step guarantees a robust and dependable platform for the solar panels, ultimately optimizing the system's performance and the durability. Next, we have mounting the modules. Before securely placing the individual PV modules on the roof, they are electrically connected to each other. The module's lead may already have plug connectors, allowing for easy connection after installation. To ensure proper water drainage and prevent water accumulation on the PV system side, the cables connecting to the junction box are placed and secured within the transverse rails. Care is taken while laying the cable to avoid any mechanical damage from sharp edges or even pointed objects. The installation process typically begins by assembling the modules in rows, starting from the top and moving to the very bottom. The first module is clamped to the rails using end clamps on its outer long edge. The subsequent modules are then positioned alongside with the previous assembled module and fastened using bolts at the middle, tightened with the screwdriver. Finally, the end clamps are used to secure the last module in the row. By following this installation process, the PV modules are not only electrically connected but also securely and safely fixed to the roof while considering weather protection and also water drainage. Next, we have running the strings through the roof. The string cables. To ensure safety and efficiency, the string cables are carefully laid within protective conduits that pass through the roof inner cladding, thermal insulation, and vapor-proof barriers. The entry point of the conduits is determined from the exterior. Making an opening at the designated location allows the cable to be drawn through the conduits using a fat coil, ensuring short circuit and ground fault protection. Employing protective conduits offers several advantages, such as enhancing operational safety and extending the service life of the cable. The conduits must be constructed from UV-resistant materials suitable for external application. Finally, the string cables are carefully routed through the ventilation tile onto the roof. Their insertion point, their insertion at an appropriate point within the roof tiling prevent rainwater leakage and the lead-through point. To maintain aesthetics, the modules are positioned directly above the tiles, and the cabling remains discreet and invisible from the outside. Next, we have the string wiring inside the building and inverter installation. The external wiring is directed to the building's interior through the shortest available route, leading to the DC main disconnect isolator switch or the PV array combiner junction box. The string cables are then directly connected to the terminals of the DC main disconnect isolator switch or the PV combiner junction box. From there, the connection extends to the respective string inverter's DC input terminals. It is customary to install inverters in a location where flawless operations can be assured. Several factors are taken into consideration during the inverter's installation, such as ambient temperature, heat dissipation capacity, relative humidity, and noise emissions. Moreover, to facilitate future servicing and maintenance, the inverters should be easily accessible and not obstructed by items like a medium-sized cupboard. By following these guidelines, the PV system's internal wiring and inverter setup are optimized for efficient operating and ease of maintenance. Last but not least, we have the installing the main connection. The AC inverters is connected to the main grid via protective equipment, for example fuses and also line circuit breakers. Also from the distribution network operator's feed meter in the meter cupboard. To start up the PV system, the meters which are connected in main circuits are set up first. All the relevant measurements are taken and recorded in the commissionary log. When the measurements are considered sufficient, the main voltages is switched on and the inverter operation is started. The inverter usually displays all the important operating states, which are then read by the operator, and from these operational values, they can determine whether the system is functioning properly or otherwise. That'll be all from me. Thank you very much.
Hi, my name is Rishen, and I'm going to talk about the design specifications and cost estimation. So here we have solar panel and PV system requiremements and the PV panel details. So for the PV system and solar panel requirements, the average monthly consumption of the school will be 1568.7 kilowatt power. And based on our TNB calculations, it would be in RM 927 ringgit and 85 cents. So with minimum of 50% savings in electric bill, it would be 785 kilowatt power. and the daily power to be generated by the solar panels is 36.64 kilowatt per hour. So for the battery type, we'll be using 2B600AH in series connection. The battery storage capacity would be 45,800 watt per hour, and the number of batteries required is 40. So for the total watt peak of PV panel capacity needed, it will be 10,776 watt peak. The number of PV panels, assuming 80% efficiency, would be 26 panels, and the optimum tilt for the PV panels is about 5 degrees from horizontal facing south. So this is the PV panel details. This is the electrical details of the PV panel. As you can see, the rated maximum power, P max in wattage, is 535. The open circuit voltage is 37.3 volts. The maximum power voltage is 31 volts. Short circuit current is 18.36 ampere. Maximum power current is 17.28 ampere. And it all happens under the irradiance of 1000 watt per square meter at a cell temperature of 25 degrees Celsius. So this is the mechanical PV panel details. As you can see, the size, solar cell, and number of cells are already presented here. So the size of each panel is 2.584 meters square, and it will occupy a total of 68 meters square of the roof space after all the panels is installed. So for the cost analysis and payback period, the estimated cost is about 194,279 ringgit 83 cents, with an estimated of 1,000 ringgit for installation fees. So the monthly loan payment would be 6,487 ringgit and 80 cents. The annual electric bill payment would be 11,134 ringgit 20 cents, and the annual profit from feed-in tariff, which is by TNB, is 8,635 ringgit and 47 per year. So the payback period is actually calculated by initial investment divided by annual cash flow or savings, which is equals to 8 years. That's all from me. Thank you.